Whether my screen is visible?
Yes, sir.
Yes, sir.
And also in between, if you get any query, put your query in the message. I'll address all those queries at the end, or if you can speak in between, do that. Okay. So today I'll be starting with another chapter in this or module. What is model building through regression? Majorly regression, and we'll talk about the linear regression. Okay. So this is actually directly not related to neural, but these are the building blocks which is used for the neural networks. So this we wanted to know. And this module is little mathematically intensive, not much, little. When I say little, means you have to uh, be careful about or you have to be clear with your probability theory. So I assume that everybody is good in probability. Can I go with the assumption and start with, or should I review the probability earlier? Hello, can you proceed now with chapter? Okay, so I assume,
Would be,
yeah, what?
so it would be good if you could just give a summary of that
Okay,
probability.
okay. Okay, so I'll just quickly rush through. Actually, this idea is not actually rush through, means just to understand. So those concepts which is there in probability theory specific concepts. So it will just understand from your memory. So it will be useful. So I'll just go through that also. So remember this probability theory, which basically is nothing but a mathematical framework for representing uncertain statements. So if something there is uncertainty and we are not very clear or firm, then we use probability theory concepts to express those ideas. Okay. So first of all, why the question comes is why probability? So possible sources of uncertainty may be there, and there are many sources of this. Maybe inherent stochasticity in the system being modeled, maybe there. When I say stochasticity, these things you are not very determining in what particular pattern they follow. It can be a very random manner. And incomplete observability. For example, even deterministic system can appear stochastic when one cannot observe all the variables that drive the behavior of the system. For example, this Monty Hall problem. So you know that it's a Monty Hall problem. It's a very old American TV program where three doors are there and the person is asked to open the door. So behind this, one will be goat or something else, and actually behind one particular thing, there will be one the actual price and all. So here you have some incomplete observability, right? So incomplete modeling using model that discards some of the observed information. The discard information results in uncertainty in the model's prediction. So this basically, I'm trying to say that though something looks very deterministic, can appear stochastic. Even this Monty Hall problem also looks stochastic. Also, there are two flavors of probability. One is called frequentist probability. So frequentist probability means you toss a coin and you count the number of heads and how many times you did this experiment. So head divided by a total number of times you did the experiment. This kind of frequency you find it, what is called frequentist probability. Then there is another flavor of probability, what is called Bayesian probability. So Bayesian probability basically it comes into picture where the concept of degree of belief related to qualitative level of certainty involves. There we go for Bayesian probability. Particularly, which I'll be talking in this regression modeling, I'll be talking about this concept, what is Bayesian probability. Okay. And also probability can be seen as extension of logic to deal with uncertainty. So this part we'll see very much in case of fuzzy also, this how probabilistic stems can be associated with the logic. Also, probability theory provides a set of formal rules for determining the likelihood of a proposition being true given the likelihood of other propositions. So this concept will also seem fuzzy, but this is in generic statement. So basic of the probability space, you know that basically it composed of three major components. One is called sample space. So you know that set of all outcomes of a random experiment. Random experiment means whatever the experiment you are doing, tossing a coin, throwing a dice, or observing certain events, whatever it may be. And set of events basically a set whose element A is in form F, a subset of omega. Omega is the entire sample space. So these are set of events, nothing big. And you know that there is a probability measure, basically which maps from the set to the real value and which satisfy the following property, which we also together call as axioms of the probability theory. So probability of an event will be always a positive number and it can be greater than 0, right? Greater than or equal to 0, but it cannot exceed 1. And the probability of the entire sample space, you know that equal to 1. And if you have this sum of all the probability, so basically if disjoint events are there, we can always sum them, so that you know that. Okay. These properties are called axioms of probability, as I told earlier. And you know that what do you mean by disjoints when no events are common and all this stuff. And there is some algebraic operations we see, some like A and B, two events of the sample space omega. So we'll denote A, it does not occur by, you know, that A complement, and like this A union A or B, which we say in set theory or particularly in probability theory. So probability theory we say A or B, and here we say A union B. If you say both A and B has to occur, so we say A intersection B, that is a set theoretic approach. And this is what we say that if two event has to occur. A occur and B does not occur. So this is basically nothing but a set difference. And set difference is represented by A intersection of B complement. So this what I'm trying to say, that this you see in normally probabilistic theory, what does it mean? And notation wise from set theoretic point of view, this is what it means. So this is fairly simple, and that you know that if probability of B is basically a non-trivial value, then the conditional probability of any event A given B is PA given B is basically intersection of this one, and whatever is conditional, so it is divided by. So basically, and this you know that is the probability of event A after occurrence of probability B. And if two events are independent, that we know that intersection of that can be nothing but a multiplied. And total probability theorem, as you know, P of B equal to PAB and P complement B, and this same way we can write for the other way around. Some B condition on A, PA plus B condition A complement, P complement. And so random variables, etc. is known to you, so I don't want to deal much about here. And you know that random variables are not the variables, actually they are a mapping function, so remember this. And so this is, and then let's quickly go through this definition on probability distribution. So a probability distribution, you know, is a just description of how likely a random variable or a set of random variable is to take on each of its possible states, right? So these are the distribution effectively. And probability distribution description depends on whether the variables are discrete or continuous, right? So if it is discrete, then it's called probability mass function. If it is continuous, then it's called probability density function accordingly. So PDF or PMF comes to very oftenly used in research papers or books, so don't get confused. And we use this notation. This is the symbol, which is nothing but similar to P. So random variable X or has or follows a distribution P. This is what it means to. And this I don't want to go. So there is some concept of CDF. So this is not very straightforward for you, not required. And properties of CDF, of course, this is the value of CDF is lying between 0 and 1. You take the limits from minus infinity, which is basically 0, and from towards plus, so it is maximum 1. So it's a CDF. And probability mass function, as I told, if the probability densities of the random variables are discrete, then the resulting distribution is called probability mass function. If it is continuous, it is called density function. So basically, this is what it. So here, if you have this, if it is f of x is CDF, cumulative distribution function, then you can always find a PDF from CDF by differentiating it. And if you have the PDF already, then you can find CDF by integrating it. This is what it happens. So properties of PDF is there. Probability density function is always greater than or equal to 0. And it is sum overall integration over the fx equal to 1. If it is a continuous random variable, if it is discrete, then summation equal to 1. And this we know that if X is one particular across A, if you are integrating, then you get the probability of this one to A. Marginal distribution. So basically, we know the probability distribution over a set of variables and want to go for this probability distribution or just a subset of them, not the entire part. Then we have something called marginal distribution. So probability distribution over the subset is known as marginal uh, probability distribution. So for example, you have a joint PD probability density probability function here. We can find just P of X with the sum rule. So sum rule means you sum across Y. But if you want only P of Y, I'll sum across the X. So this is basically if the probability is discrete, random variable is discrete. If it is continuous, accordingly you integrate either with respect to X or with respect to Y. Okay. So that's, and then there is a multiplication rule. So joint probability of a set of random variables can be expressed as something like this. So you have this joint probability if you want. So p of x and I equal to 2 to n. So here basically y is taken from 2, px1 is there, and then we multiply. So 1 given 1 has already occurred. This is I. If I want to say 2, so 2 given 1 multiply another one, 3 given 1, 2 comma, like that it happens. So like see here, so three random variables are there, so it's a joint PDF. So you can apply this multiplication rule, says px1 px2 given px1 given x1, like x3 given x1 comma x2. So this, some of the things are there, and there is a independence and conditional independence, these rules are there. So this is pretty clear, so it should not be a problem here. So two random variables x and y are independent if and only if you know that if the x is from x and y, and if we can multiply them, they will be independent. And also they are conditionally independent given a random variable z. So it says that if is x and y given z, if I can write x given z and y given z, then this kind of probability basically is called conditionally independent. And notation Vx inverted norm y means that x and y are independent. Sometime I have shown you this notation used when showing the two vectors are orthogonal also. And if you say conditionally independent, then you say that x and y are conditionally independent given z. And there is a quick definition for expectation, variance, and covariance, because these three terms we use oftenly. So expectation is nothing but it's basically statistical mean, right? So expected value of some function fx with respect to probability distribution p is the average or mean value that f takes on when x is drawn from p. And this is normally, it is written as nothing but p of x. And if it is discrete, then we just sum it off. And when if it is continuous, then take the integration of it. And this is how we denote that expectation of when x is distributed p and we want to take the expectation of x. So this will be used. So as I told, if it is continuous, something like this, integration will happen. And also expectation operator is a basically linear operator. So if you have a linear combination of fx and gx, and if I apply expectation operator over that, it means alpha times e of x fx plus b times e of x gx, where alpha beta are some constant from real set. Or then the variance gives a measure of how much the value of a function of a random variable vary as we sample different values of x from its probability distributions. We want to say that how much variance will happen, the whether same, and we know that when the variance is large, what will happen? There is a lot of variation in the values. And so variance of fx is formally defined as this expectation of f of x minus starts expectation of fx and the square thing. So you can say that nothing but f of x minus is mean, and then you take the square of it and find the expectation of that. So this the definition for this variance. Variance is low, the values of x's are clustered near its mean, as you know. Basically, you can say that if I'm talking about in terms of Gaussian distribution, so that bell curve will be there, so the entire curve will be falling near to the mean itself. And when you know that variance is large, so it is basically spread out. So in standard deviation, you know that this is the square root of variance. Also, standard deviation is basically a Euclidean distance between the values of fx and its mean. And this is the last statement in this I'll be using, less then we'll resume the class now. So covariance gives some sense of how much two values are linearly related to each other, as well as the scale of these variables. We'll see this. So covariance basically for two function f of x and gy. So expectation over entire thing. So expectation over, you can say that multiplication of variance and then you are taking this, but not exactly variance. Fx minus e of fx into g of y minus e of gy, and then you're taking expectations. So this is you're finding covariance. It says that basically you're finding some sort of a relation between the two, how they are related to each other. High covariance means that the value change very much and are both far away from their respective mean at the same time. And positive sign of covariance means both variables tend to take on high values simultaneously. Negative sign covariance means one variable take to high value at the same at the time that others takes on low values. So and the vice versa, of course. Measures such as correlation normalize the contribution of each variable in order to measure only how much of the variables are related, rather than also being affected by the scale of the separate variables. So there are many things. So for the class, today's class, this much is enough. So I start with this. So just we wanted to know this, what is the probability space, what are the probability axioms, and what is the conditional and independence and normal independence, then expectation, variance, and covariance. And with this, we'll start now. So when I say model building through regressions, basically we'll talk about many things over here. And as I told, don't get scared of this one. This is little intensive, but of course it's beautiful as well. We'll try to understand because so many of you used off-the-shelf regression modeling or regression, etc. But sometimes you don't realize really what is happening inside from probabilistic view. So we'll see that. So basically the idea of a model building finds application in every discipline that deals with statistical data analysis. So when I say statistical data analysis means you are observed certain events and you know that when this attribute is there, this event happened. And many things observed, but you're not able to find what causes this kind of thing. So basically this data is very statistical in nature. You don't know why it's statistical and stochastic because you're not very sure how it has been modeled. So wherever such kind of stuffs are there, model building is very much part of it. So for example, we are given a set of random variables and asked to find relationship that may exist between them, if any. When I say random variables means here that could be anything, but let's say a training set is there where three attributes are there and certain desired values not given to you. And from one particular event to the another event or many other event, you are not able to come out with very clear-cut relation. So how do you go about this? So this kind of relation, if you want to find, so what to do? So then we'll do when C and regression also. If you remember that I talked about a few classes earlier, in this basically machine learning, or the neural, basically two classes of learning problems are there. One is called regression, another is called classification. Many other are there, of course, but these are the two major things. So regression, when you are going for some sort of prediction of this some continuous value, and classification as usual, you know that if already labeled existing labels are there, so you want to know whether the current input which I'm giving, which label it belongs to. Okay. So regression basically is a special form of basically is nothing but a function approximation to model given set of random variable. If you remember that the entire neural network part is nothing but function approximation, means a black box is there and you want to know what causing this, what kind of function is there which is causing this input attribute to be translated into such kind so and so desired value. So it's nothing but function approximation only. So regression, what you're saying that is a special case of that. And in regression, we typically find the following scenarios. And so one of the random variable is considered to be of particular interest. And that random variable is referred to as a dependent variable or response, or what we call as a desired output, or the response you can say, or sometime target. Also, so the remaining random variables are called independent variables, or here independent variable instead of SAT, statistically people call it a regressor. in case of regression analysis. And the dependence of response, that is y, simple to say that if I am saying y equal to f of x, so x are nothing but regressor and y is nothing but this is something called response variable. So dependent of response on the regressor includes an additive term, error term, to account for uncertainties in the modeling, which is the dependence is formulated. Or you can say that a error term is always added because there may be something, some phenomena which we may not be able to model. To account for that, we add this error term. And this error term is called either expectational error or sometimes we call it an explanational error. And broadly, there are two classes of this regression. One is called linear, another is called non-linear. So linear class regression is mathematically tractable. Non-linear is, of course, it is, but it takes a lot of efforts to do that. But majority of the time, we'll be dealing in this particular course with the linear regression only. Okay. So today I'll complete this part for the linear regression only, not non-linear. We'll see the non-linear part later if time permits. So this is a very abstract view of a linear regression, how it may be. So you have a regression. So simple to say that nothing but the input vector, and you have desired output or the response, you can say that, or output, which you are denoting by D. And there is a system in between, and this is a black box, and I don't know what is that. So that's why I'm saying unknown stochastic environment, which is nothing but some sort of function is working over there. Only thing is we don't know what is that, right? So, and in that particular, if for the linear thing, we know that when I say linear means some sort of linear combination of weights with the regressor. So, but what is not known to is this weight. What is that particular weight? So if I just open this particular model from linear perspective, is nothing but sum of the linear weight, the linearly weighted sum of the input attributes. You can say W1, X1 plus W2, X2, etc. And as I told earlier, there is another term which is E, which is nothing but what we call as expectational error or explanational error. And this is added to account for some of the modeling assumption which you have relaxed or something we have not accounted for. To take into account, we use this E. And then finally, the your desired response. So this is how a linear regression basically looks in a very abstract and in a simple signal flow graph. Now the environment is probed by applying a set of inputs and constituting the regressor. So finally, it gives you basically all this x1, x2, xm. So what I'm trying to say that if your one input is there, if your entire training set is there, so and if it is, it depends on the three attributes. So this is nothing but x1, x2, xn, x3 could be. If you remember, I was talking about the toy example of rent prediction system in Manipal for the students. So basically, it's basically R5 to R1 problem. Basically, R5 to R1 problem is a function map, the F you want to find. That there are five input attributes: the number of bedroom, washroom, walking distance from your home, the place to the college, and parking space is there or not, garden is there or not. So these are the attributes basically. So in that case, if it is M is nothing but the 5, right? So, and then desired response is considered to be scalar for the convenience, but it could be vector as well. The toy example which we are considering a rent prediction system for students in Manipal, that is also a scalar value, which gives you final rent. What is the value comes out to be? So it's a single value, not a vector. So we don't know the functional dependence of D on the regression. We don't know. So we propose a linear regression model which can be parameterized something like this. We assume that, let's say, because we are talking about the linear regression. So D as in nothing but the linear combination of W and X, this one, and plus a error term. Now, this all W's are also, there's a set of fixed weight, but only thing is that these are unknown, and that's what we are looking for. These are the parameters, unknown parameters, meaning that environment is stationary. This set are fixed. These are fixed. It's not changing every now and then. That's why I say that this stochastic environment is stationary. There are many things. There is something called stationary and non-stationary. Non-stationary means your things are keeps on changing. like you can see temperature or pressure in a day. You cannot say it is stationary, it's a fixed morning to evening is same thing. It changes every now and then, right? So this is the stationarity. Only thing is that if you're not measuring it probably, so but this over the period of time, if it is changing, so it is non-stationary. If it is remain fixed, that is stationary. So the term epsilon here or error term E represent the expectational error of the model, which accounts for our ignorance about the environment. As I said, something is there which you are not able to model. To that particular ignorance to account for, we use this error term. Also, so when we write this, finally everything has to be boiled down in matrix notation for the ease of convenience and the analysis. So we know that it's basically dot product between W and X, which I can write as a just inner product WTX, and of course E is there, we can write it down. So this entire part comes out to be in a single matrix notation in this way, WTX plus epsilon. Also, the common dimension M. Common dimension M means the dimensionality of the input space or dimensionality of the parameter space, that is W, is called a model order. So suppose if you have a three parameters, we say that the model of the order of the model is 3, 4 accordingly. Also, so with the environment being stochastic, when I say stochastic means probabilistic and its changes, we are not very fixed, sure that what the value will be. So it follows that X, W, and E are nothing but the sample values. Sample values means they're single shot realization of a with vector, that is entire, you can say that input space X, an entire desired space D, and entire error space E. So it's a single shot relation of that, means one sample from these vectors. Now, when one sample, so here I just want to tell you this, you should not get confused, means what do you mean by single shot realization and all those things. So let me go through this one simple uh, visualization of this. So I'm just saying that like our own this toy problem which we am talking about, and I said that it's nothing but R5 to R1 problem. So means you have input spaces here, your X is 5-dimensional and D is basically 1-dimensional, right? So suppose before the system to design, you have moved around entire area and you're trying to find the values. So X1, X2, X3, X4, X5, and you ask the people, means what is the rent you'll be taking off. So let's say this is example number 1. So you got this value, this value, this value, and this one, and value 2 for this like. And accordingly, there may be some error you are accounting for. In this case, some error may be there. Here, some error will be there. Likewise, this entire piece. So entire set of your training vectors, suppose you have surveyed some 1,000 homes in and around Manipal and you created this kind of data. Of course, this is not known to you, so you'll be randomly choosing some value for that. So this entire part will create your X, what is called a design matrix, and there's a D, the entire vector. So you can see if 1,000 homes you come across, so the dimension of this X, the design matrix, is nothing but 1,000 cross 5, and when you went for this, so your D vector, where the desired value is also basically is 1,000 cross 1, and of course epsilon is again is a 1,000 cases and this basically a single values is a vector, right? So when I say this small X, W, and epsilon is basically single shot realization of this, means only one example you are taking, one instance, first, second, third, any one particular. So this is single shot realization from the largest set. This is what we need to say. I hope it is clear. And if not, please ask a question. Is that okay so far? Whatever we have discussed?
Yes, sir.
Okay. With such a stochastic setting as a background, the problem of interest may be stated as follows. So we have entire background you have set up. Now, what is the question we want to ask? So question is something like this. given the joint statistics of regressor X, nothing but our design, this one, that is the design matrix X, and the corresponding response D, estimate the unknown parameter vector W. This is what we normally do. The whole idea is that we have to find this vector W. And in this case, it's not vector anymore, rather I should say matrix. Okay. So this is the problem. And you see that joint statistics of regression D and W. When I say joint statistics, what we really mean is following. Means that we are given to us, or we are able to find correlation matrix of the regression X. We have seen how to find the correlation. Then the variance of the desired response D. We also know how to find the variance. And the cross correlation vector of the regressor and the desired response D. So this is what you mean by the joint statistic is given to us. So based on this, is it possible for me to find a value of W? So this is the question we are asking now. And can we estimate it? And that's what. Yeah, there is no way we can actually calculate it in the closed form, but we always go for estimation. Any machine learning or neural network thing, if you are doing some sort of a fitting, it is always an estimate, not the exact. Also, it is assumed that the mean of both the regressor and the desired matrix vector is 0. So there is a concept. So when we apply this Bayesian approach, there is some concept, something called maximum a posteriori estimation of parameter vector. So something what is in short called MAP. There is something called MLE, that is maximum likelihood estimate. So that's basically is one approach, and this MAP is another approach. So we'll try to understand and see, compare and contrast between the two, MLE and MAP, which one is better under what situation and which is more accurate. Okay, so we'll see that how. So Bayesian paradigm provides a powerful approach for addressing and quantifying basically uncertainty that surrounds the choice of the parameter like W in the linear regression model and or anywhere else. So regression acts as a basically excitation. When I say excitation means it has no relation to the parameter vector W. Because this X does not decide W. So what decides the value of W is nothing but information about the unknown parameter vector W is contained in the desired response that act as an observable for the environment. So basically, the information for W is actually is in D. So accordingly, we focus on the joint probability density function of W and D conditional on X. We say that, okay, we want to something like this. So here we are saying that joint probability density function P subscript WD given X. There is a notation I'm saying, but actually in bracket WD given X. So this notation we'll be using, and we know that from probability theory, we can always write something like this, that probability density function joint probability W X given D also can be written something like this. WD given X and PD if I multiply, it gives the same thing. And equivalently, I can say this way, Wx given D. So D given Wx, so D given Wx. And when I say this, I'm multiplying by PW. So one and same thing. It means another way of saying, not the same, but there is another way of saying the things. But both these things will have a same value. So I can compare this with this, and finally you'll be able to find something. So when I say compare this with this, so ultimately what I'm looking for is basically probability of W given the D and X. Means D and X is nothing but the entire training set, where desired response is known to you and the input attributes are also known to you. So this is how so you can say compare this and this, means this kept equal to this one, and then this part divided by PD. This part is going, and of course you make assumption that PD is not equal to 0, otherwise the entire part will become finite. Okay, now so this last equation is special form of Bayes theorem. Basically Bayes theorem we have seen, but it is a bit different way it is written. And it embodies basically 4 density function, and we are characterizing them one. So 4 density function 1, 2, 3, and 4, and we try to understand what are those. So first one is observation density. Observation density is like this one. Means observation means what is the response part. So probability of D given weight space and X is an observation of the environment response D due to regressor given the parameter vector W. So this is basically called observation density, PD given Wx. Then there is something called prior probability. So prior probability is nothing but P W referring to the information about W prior to any observation made on the environment. This is there. Without before observation you have this. Henceforth we'll be denoting this prior probability by pi W. It's just a notation. We could have used any other function as well. Then there is something called posterior density. Posterior density means basically something W you want to find given these values. So D and X is known to you from the given the environment. When I say environment, what I mean to say training data available to you. So referring to the parameter vector W, after the observation of the environment means D is there. Observation of the environment had been completed means you have seen that for this many X, what is the value? And henceforth we'll write pi W given dx. And then there is evidence. Evidence means you want to say the probability of the desired response is what will be value. So these are the referring to the information contained in the response D for statistical analysis. You can always find it. It's quite easy to do that. So this particular this one has 4 density, or you can say probability space, probability functions: observation, prior, posterior, and evidence. Now this entire part, these things, we can write in a more simpler form, and we can write this is in terms of likelihood function. And please note that I want to clarify here, many of us, we have confusion that likelihood function and probability density function are same. It is not so. There is a slight difference between the probability density function and the likelihood function. Remember that when I say density function, so integration, or you can say sum of the entire density function equal to 1. But it may not be true for the likelihood function. First of all, likelihood function, it may not be integrable at all. And also when it integrates, it need not to be equal to 1. And also in likelihood function, we want to find the probability of the parameter with the fixed observation, or the basically X, you can say that, or the data values. So we'll see. So observation density is commonly reformulated as a likelihood function. So we are writing this D given Wx is a P LW given dx. As I said that likelihood function we are writing in terms of parameters, assuming that X is fixed, that is the data is fixed. And this is, we have already seen this. Now, as far as the estimation of W is concerned, the evidence probability of the response in the Bayes relation plays a role of normalizing constant. If you see this in this particular, it's basically worked as a just normalization factor. So nothing else plays. So I can just ignore it also if you want. We can ignore because just X a normalization factor. Then we see that P W given dx is some sort of proportional to multiplication of this and this, and we have used some sort of notation to write this function, so we can write it across. So this is, so we may express the Bayesian relation here as the posterior density of the vector W parameterizing the regression model is proportional to the product of likelihood function and the prior. This and the prior. So if you see here, this is your likelihood function and this becomes your prior. And because this is a constant, so I'm just ignoring it. So this is directly proportional to multiplication of this and this. This is what it has been said. And because we use this pi notation, so we'll include henceforth to simplify our work. So pi W given D comma X proportional to L and pi. So we'll see this. Now the likelihood function L W given dx provides the basis for the MLE, the maximum likelihood estimate of the parameter vector W, and it is shown as something like this. That if likelihood function is there with you, you calculate this R max W. So this notation I have already talked about in case of linear, when I'm talking about the linear algebra also. Can anyone of you tell me how to calculate this or what to do here? Anyone? What's supposed to be done here? Hello? So you say that this is f, so some sort of function L, and these are the entire part in the argument. So it says that that value of the argument with respect to W, which maximizes this function. So how do you know that? What is that value? If I write here x and here f of x, what do you mean by that? How do you do it? It's simple to say that that value of x which maximizes this f. So it's nothing but find the derivative of this, equate to 0, find the saddle point, and that particular saddle point actually it is indicating the peak, and at that particular peak value you will be able to get the maximum value, right? At saddle point you will be going to get the maximum. So this is how you will be able to find it out. So this approach, what is called MLE, that is maximum likelihood estimate. Remember that always whenever you have to do the maximum likelihood estimate of any function with respect to some certain variable, so you don't have to do anything else, just take the differentiation of that particular function with respect to the variable with which it has to be done MLE and equate to 0. Find the stationary point. Once you find the stationary point, substitute that will be the maximum value. So if actually you are finding those W itself. Now for more profound estimate of the parameter vector W, we look to the posterior density W given dx as well. So we'll see that. Now we are defining something called maximum or posterior estimate of W by the formula W map. So when I say this R max pi W dx, so remember that earlier we are writing in MLE only the likelihood function, but here we are not putting likelihood function, rather we are doing this posterior function entire thing. So this we have done, and you know that it depends on the likelihood as well as the prior, right? So map estimator is more profound than ML estimate due to following reasons. First of all, it's a bit illustrative. The Bayesian paradigm for parameter estimation rooted in the Bayes theorem and exemplified by map estimators exploits all the conceivable information about the parameter W. Means whatever you have written here, that is equal to this one multiplied by whatever. So one is W information is already encoded in the likelihood function, but W information is also encoded in the prior information, which is ignored by MLE, but it is not so in case of map. So you are considering also the whatever information, all the conceivable information about the parameter W. So even that also taken into account. In the contrast, as I mentioned, in ML estimator lies on the fringe of Bayesian paradigm, ignoring the prior. Prior is not considered here. If you say that, here only this likelihood function is considered. But when I take the map, entire part means even pi of W is also considered. That's why we say it's a more profound estimate of that. Another is that ML estimator relies solely on the observation model DFX, means a training set, and may lead to a known unique solution if you apply this MLE. To enforce uniqueness and stability on the solution, the prior has to be incorporated into the formulation of the estimator. So which may not be case in case of MLE, which is done in map estimator. So you can also say that what's the difference between the two, map and MLE. Now we'll go for this parameter estimation in a Gaussian environment. So you saw that how linear regression we've been modeling, and from linear regression we wrote this Bayes equation. From that base, basically we formulated this equation for MLE, equation for map. Now we want to say that if the environment is Gaussian, means with some particular probability distribution we have to talk about. If the environment is Gaussian, then how do I estimate the parameter? Means how do I find the values of W? As simple as that. How do I estimate it? So first we are considering that this entire training example means what would maybe the size maybe let's say n samples are there, xidi. So to proceed with the task of parameter estimation, we make the following assumption. Some assumptions we make. So first one is statistical independence and identical distribution. We say that n examples are statistically independent and identically distributed, right? So how should I say? So there is a group of this values or the training examples. So if I am drawing, let's say a random at random anyone, or let's say first one, and I'm saying another I'm drawing second one, they are independent, means there is no relation that if I'm taking one, then next will be two only. I could have taken anything else, or there's no relation between the two. There is no either linear relation or temporal relation, nothing of that sort. So this is basically statistically independent. And when I say identically distributed, means you cannot have that you have a training examples, let's say 1,000 yeah, examples are there. Some 50s are having Gaussian distribution and some 900 are having say Bernoulli distribution, another 50 having say Boolean distribution. No, all should have the same distribution. What I mean to say that, suppose if I am saying if you do particular study for some policy to be designed at the national level, so you have to ensure that it is applied throughout the pan India, right? So I cannot say that it is if a policy is framed for let's particular northern state, and if I'm trying to do some analysis on the people from the southern, it may be wrong because it is not identically distributed. So this entire data set on which this policy has been framed, etc., they should have take a representative group, and this group should be belong to the same kind of behavioral group, etc. So if you're talking about the entire India, then if people should be from Indian subcontinent only. You cannot take somebody from Africa or from Western world and do some kind of study. No, it's like a different distribution you are pitching it. So remember that is IID, independent and identically distributed. What do you mean by that? Then there is a Gaussian concept of Gaussianity. You are assuming that the environment is Gaussian. So responsible for the generation of the training data, whatever it may be, is Gaussian. Ultimately mean to say that if there is an error term in that, it is Gaussian distributed with zero mean and variance sigma square. And of course, I equal to 1 to n, as many as examples are there. And you are also assuming stationarity. So this is a third assumption. So the environment is stationary, means that the parameter W is fixed, only thing is unknown throughout the end trials of the experiment. That's why you say it's a stationary. And so there's three assumptions you remember: IID, Gaussian assumption, and stationary. And then we assume that the weight space, whatever the weight space, if there the PDF is there, and that PDF is also Gaussian distributed with the zero mean and sigma square, and of course W means this has to be shown that is the variance of the weight space. Now, let's say for the ith trial of the experiment performed in the environment means for one example, means one desired response is there, so which can be mentioned in WTXI plus epsilon I. And of course, these are nothing but single shot relation from dx and e. And remember that here, just to have some sort of clarity and differentiation, because e is a vector of all this error, expectational error. So normally, if that was not the case, I would have used e for expectation as well. But just to differentiate with this expectational error with the expectation operator, so we have used as a boldface e, right? So and this particular boldface e, I should say Blackboard script e denotes the statistical expectation operator. And due to Gaussianity assumption, we know that already I mentioned that the error space has got zero mean. If zero mean is there, so we'll talk about the variance. So variance, we know that basically e minus mean of that and the square. Because this is zero, so this is nothing but the sigma square only. Variance is sigma square. And now for the given regression xi, let's see that what is going to happen. So let's see this. I want to find this for regression is there. What is the expectation of di? Why I'm saying that, because I need for that thing. So di, where di is nothing but d is nothing but wtxi plus epsilon I. This one is there, right? And when I go for this, and in the probability revision slides, we have seen that E expectation operator is a linear operator. So we'll take it inside. When I take it inside, it looks like something like this: E of WTXI plus E of E. Now, just now we have seen that the mean, statistical mean of this error vector is 0. So this part will become 0. And remember that here WTXI will give a scalar value. If you give a scalar value, then the scalar value is nothing but a constant. The expectation of a constant is the constant itself. So this will comes out to be WTXI. Okay. Now, if that is the case, we want to find the variance of D as well. So variance of D, as per the definition, we know that variance we have seen in the previous few slides, well, for review slides, di minus E of D, where I mentioned fx minus E of fx the whole square. So here instead of fx, we have di. So di minus E of D whole square. And now instead of E of D, E of D is nothing but WTXI, and DI is nothing but WTXI plus epsilon. So WTXI plus epsilon I minus WTXI, this will go, only the EI is left. So for that, if you square, that is nothing but square I, and this is nothing but sigma square, right? So this is nothing but sigma square. So you know that. So ultimately, it's saying that the variance of the desired response and the regressor is variance of the regressor and the variance of this error is nothing but sigma square. And this is obvious because we have made such kind of assumption itself. Now the likelihood function for the ith trial is defined because we have mentioned as per the assumption 2, that is that it should be Gaussian. So when I say Gaussians, 1 by root 2 pi sigma exp 2 by, and remember that we are talking about here di minus mean, whatever means this one part is there. So minus mean is nothing but, we saw that it is nothing but WTXI. So that's why WTXI square. So this is the basically this has come due to the likelihood definition of the Gaussianity. And now we are invoking the IID characterization of the n trials. So the first assumption we made that the random variables are uh, statistically independent and identically distributed. Whenever it is IID, so whatever the likelihood functions are there for what many samples, you simply multiply them. So you know that this capital pi is nothing but indication of multiplication. So you simply multiply them. When I multiply it, so we write something like this. For one particular instance of this is written. So we'll just write it across like this. We substitute the value of LW psi from this equation over here. So 1 by 2 pi sigma, this entire part. Now, what I can do this, if this is a constant term, if I take it outside here, what will happen to it? If I take this constant here before this pi, what will happen to it? Can I do so? Hello? May I do so? If yes, then what is the value over there?
To the power n.
Yes, because it is going to be multiplied n number of times. So this is power n. So we have this one. Now can I swap this exp and can I get rid of this pi somehow? Is it possible? So this is simple to understand. This is nothing but product of exponentials. And product of exponential is there. So you remember that product of exponential is nothing but the exponential of sums that we can do this, right? And this is how exponential, and then this is a constant term which will goes inside and finally sum over all this thing equal to 1 to n, whatever it may be. So this is how a likelihood function you are able to characterize it. Now, so all this story that we are building upon is finally to find a value of W using this map. So as I mentioned this, accounts for the basically this LWDX. You have to consider the entire space. So accounts for the total empirical knowledge about the weight vector W contained in the training sample T. Total empirical knowledge means the entire training data is given, which is that this has been accounted by this particular formula, or the relation I should say, not formula. Now the other source of information that to be accounted for is contained in the prior PW PyW, and we know that we are doing this for map sake only because it gives more profound estimation as compared to MLE. Now when we go for this, so also we assume that W is having W is also some sort of distribution is following, right? And we assume that it has got a zero mean. And following IID characterization of the M elements, we said that all these M elements are basically IID, independent and identical distribution. So we may write this also something like this. This I equal to 1 to M, and these are independent. So this is nothing but probability only. So we can multiply all the probability. When I do this, so pi of W and pi of W I mentioned basically that is also Gaussian assumption is there. So 1 by 2 pi sigma W. So this is nothing but the standard deviation of the weight space, and exp minus Wi square 0 2 sigma square, where here we have not taken any minus for the simple fact that the mean is 0. And this same thing when I take it outside and m number of terms are there, so you multiply it by m. And remember that when I see m, this small m, this is nothing but it's indicating the dimensionality of the weight space or the basically attribute space. Both are same here. And when I write capital N means how many examples are there. So this is the difference. So this is the again we can flip it up with pi is there and exponential. So I can write the product of exponential. Instead of that, I'll say that exponential of sums, which we can do very easily. So this is what we have done. So pi of W also we got it, and likelihood function also we got it. Now we find the estimate. Now see, and this remember that this particular part we can always write it in this particular in the Euclidean form, and this we have done it for a particular reason that this is a vector notation to do that, and this explanation I have already given why is it so. Now with this we'll see that we substitute for LW and pi into this particular equation which we have seen earlier. When I do so, so this part here we write for pi WTX, and for here pi W we mention this particular part which we have just derived or wrote in the previous slide. We have done this. Now when I multiply this, these two things are constant. This is constant, this is constant, whatever the value may be. Because of constant of proportionality is there, we don't bother about this constant factor. We just write proportionality ignoring these two terms, and we say that this and this basically exponential is again is a product of exponential, so I can write as the exponential of sums. So this plus this, okay, this is what it comes out to be. When this comes out to be, then it becomes as per the map definition we saw that. And remember that here because it is you're dealing with the exponential, so and whenever this estimate is done, it is better to go for taking the log of that, for a simple reason that basically log is a monotonically increasing function, and it's by making use of it, it is does not affect the overall the information which we are going to infer, but at the same time it makes our life simple to deal with this exponential, because log, when it's considered log, is a natural log. So natural log of exponential is nothing but the 1, so it gets nullify about it. So argmax log for this, so let's find log of, when I go for log of pi wx, so it means this one, so this entire exponential will get rid of it, and what we'll get is something like this. So we have this particular thing. Now we got only this part. Now we are left. So this is basically argmax w, let's say f of x. Once we are done with this, so job is very simple. I will take the differentiation of this entire particular function, equate to 0 and solve for w. If that is the case, and then we are done. So let's see how do we go about it. So let's see. So this particular part, Now to make our life simple, so this get rid of this variance. So I'll multiply variance sigma square here and here. When I multiply by here, it becomes 1 by 2. When multiply by here sigma square, it becomes sigma square over 2 sigma square w. And then this entire sigma square over sigma square 2. This I'm calling some sort of variable lambda. I could have taken anything else also. So I put lambda, and this is how it could be. Now this entire function is known to you. This f of w is given to you. We have to write it in some fashion so that I can differentiate it. Now here we have to, let's call this particular, whatever the term is there in the bracket term, let me call E of w. We couldn't take anything, but I'm just using this notation from the book. So for that, to in compliance with that, so E of w, and remember that I'm considering here only the positive part. Let's say minus we have taken common, so this is becomes positive. So E of w is there, something like this. And so remember this maximization of the argument in map means, because if I here thing is that maximization and this is the negative term. So negative of x, if I maximize this, is as good as minimization of only this positive term, right? So something like this as mentioned here. The maximization of the argument w is equivalent to minimization of EW, right? So this is what I mean to say. So I have to find that value of w which is going to minimize it. Now it's mentioned that optimum estimate is obtained by, as I mentioned, differentiating this and equating to 0, right? We obtain the desired map estimate of m cross 1 parameter S vector. So it becomes Rxxn plus lambda I inverse Rdx. Now the question is, in book it stops here, from where it came. So we'll solve it now. So we'll go for this particular result from where it came. Before that, I need to tell you something about. Hello?
Can you explain why we took it as positive and not negative,
Okay,
like the
okay.
equation?
Yeah. Here, right. So why we have taken positive, not negative? We could have taken that way also. There is no problem with that. To make my life simple, I'll take this minus common. If I take this minus common, so this entire part become positive. I can take it as a f of x, right? Anything it could be. Now here I'm saying that because entire part has to be maximized. When I say maximize, so maximization of a negative function means what? You want to find that value which is near to 0. So we are maximizing this. Your maximization of this negative function is as good as, if you're taking this f of x, is as good as minimization of f of x. There is no other reason for that. It's just the sake of convenience. So we have taken this particular part. If I just put minus here, that is also okay. No problem with that. Is it okay?
Yes, sir.
So, okay. So here I said this this one will do, and we found this one. But the question is how to find this. Means how from here to here we get, and that's the beauty, and that we'll see now. So but to understand this, there is a concept, something called matrix calculus. So there's completely one or two lecture I taught in matrix machine learning on matrix calculus. But here I'll give a quick shot that matrix calculus is nothing but, you might have heard of integral calculus or differential calculus, where you will differentiate or integrate over the function. But matrix calculus means what we do, we differentiate a matrix with respect to a matrix itself. How do we do this? So certain notations we have here. So first of all, let me say this f function, which is a m cross n, means there is a matrix, which is there is some sort of function which maps a matrix into a scalar value, right? And then we want to find the gradient of w. When we say find the gradient of w with respect to a, where a is a matrix itself, then is a basically the resulting thing is also a matrix of partial derivative, and we define as a dou f by dou e11, dou f by dou 1 2, like this, right? So just hold on for some time. I'll tell you where to use and how to use. Then let's say a m cross n matrix is there, and ijth element is nothing but dou fa by dou aig. We find it. But if a is a basically a vector, n-dimensional vector, let's say, so dou fx1, fx, So do x1, do fx, do x2, etc., etc. Means ultimately is saying that whatever the vector is there, differentiate each element with respect to the different element of the x vector. Just a minute, something. Okay. So we have, before going into more detail, so something like this, and this gradient is nothing but a differentiation. So instead of writing d of something by dx, because you're talking about differentiation of a matrix with respect to a matrix, we write as a nabla, not nabla. It's a nabla. It's like an inverted delta symbol. So nabla, so we are differentiating btx with respect to x. Remember that b is a vector, x is also a vector. When I differentiate it, the value comes out to be b. So I'm not going to detail about this. For the timing, you can just remember it and we'll make use of it. So how actually exactly it happens here? So this I want to tell you so that I'll be making use of this particular notation, so should not get confused. Actually, whenever this is a linear equation, right? So whenever you have something like a b is there, right? Is a b1, b2, let's say b3 transpose, and there is a x, say x1, x2, x3, whatever it may be. And might be I might have written this btx, and if it is required to find differentiation with respect to x. So always, because is x is there and this we have to differentiate with respect to x only. So remember that whatever the constant factor, the previous one factor comes out to be, which is independent of the x which we want to differentiate it, we write this as it is, and above that we apply t. So whatever this I am saying in a very generic sense. So that's why it becomes b. If you otherwise the formula is something like this. If I say btx, say b, but how b came, then you may forget later. Means t has to be removed. But sometime t won't be there. Then you have to put the t as per this particular formula. So this will make use of this. Don't worry about it. You see that. And there's another, this is a quadratic equation form. This it also I have told you in my linear algebra slides when I will talk about this. That is nabla x xt ax. This is nothing but a quadratic equation is which comes out to 2ax. And then when I see nabla square xt ax, which is basically a double derivative, sometimes we call it Laplacian, so it becomes 2a. Okay. Now with only this much information, if you even if you don't understand it, it's okay, but only if you remember this particularly this two relation, will be able to solve this, or I'll be able to convince you how we derive from those things the bit space. So derivation detail we are going to, so we have written e of w. Again, I am visiting to that because ultimately I want to find that particular value of w which is minimal, which minimizes this particular function. Now, so let's consider one example case, because here we have taken an example case. I'm considering only one example case. And remember that this is basically square. So square form, if I remember, I told you in the linear algebra review that whenever square is there in vector notation, it is as good as the xtx. So 1 by 2 constant factor, let it be di minus wtxt, this one, plus lambda 2. And because of this one is there in Euclidean square, if we can always write WTW. This also I've explained you with the analysis how it came out to be, or why is it so, or why is it equivalent. Because why I'm writing all these things in terms of this, because everything is in vector notation and I'll be applying matrix calculus to it. So find a derivative. Okay. Now before we find a derivative, we'll try to solve this function as much as possible. So what we'll do, we'll take t inside, dit xitw, and basically this is there when you take t inside, so it flips the position. Okay, so this is simple thing, we know that. This is also I discussed in linear algebra review class, and this remain as it is, and lambda 1 by 2 I've taken common, so it goes out lambda wtw. Okay, now we go for further, then we just keep on multiplying. It's a simple multiplication fact, so we keep multiplying with this. And when we multiply this, and remember that this is basically just a constant term, so it doesn't affect, but let it be like this, no issue. Now let's see that if you remember that we have to differentiate with respect to W. So whatever the terms comes, the W should be in a differentiation position. What I mean to say here, wherever you saw X, this location should be replaced by W. Means here, if I want to differentiate with this single derivative, then it should be here W, here W. Here also W, W rest in between matrix can come. So with that into mind, so let me see that. Can I do something with this? There is something DIT WTXI, XIT WTI, and something like this. Here, whatever the we want to differentiate, it is coming in between. So what I can do that I can flip these two positions. I can flip this to become WT and this becomes XI. And this part also has to be flipped because you know that this is going to be quadratic equation. So this also has to be flipped. So I can say XIT and W. This is okay. It is already in that particular form, so we can solve it without any problem. So here also, this W has to be shifted here. Shifted here. So what we can do this, I can flip this across. Flip this across. So I can write XI, XIT, and this is becomes W. Similarly, this W has to be flipped here. When I flip here, what will happen that DI becomes T and becomes this one W. Let's see this how we do it. So after doing this changes, Xi, Di, T, two things are common here. We are writing this. Here I can write W will be here. Similarly, W I'll take it here. So these two things I observed and put it across the two Xi, Di, Tw plus. As I told you, we are flipping it and accordingly transpose position also will change. Here also change. It becomes Wt, Xi, Xit, W plus lambda W2 W. Now life is simple. Life is simple. So I'll show you with the board so that it becomes a bit clear. Means why I'm doing something and how it is done. So let me just put it on the paper so that I can just show it to you. This vector. And I have, okay. So now we have simplified in proper way, and now we are ready to apply the nabla, means that the differentiation operator process. Now let's compute nabla, means the derivative of this. Ultimately, what we'll do in order to find a w or r mean this one, we have to integrate, differentiate and equate to 0 so that the value of w will be able to find. So when I do this nabla w, we'll apply nabla w over entire. And you know that differentiation is a basically linear operator, so it goes one by one to each one. I can take this nabla inside easily, just like you do dy by dx if you differentiate across the sum of the variables, right? I take inside something like this. Now this is what, remember that I shown you something called nabla x btx, and that was say the value is b. So here is a nabla w xi di t w. So it is entire xi di you treat as this is b, and with respect to w, so this value comes out to be xi di. That's all. Of course 2 will be there, plus if I remember I said this nabla x xt ax. So this entire part you consider as a, right? A, and this entire part basically you are taking single derivative, so it becomes 2ax. 2ax means 2xi xit, x means w, plus this is also here. If it is nothing, w is basically something like this is lambda. Lambda can be taken out, right? So I have written I think here. So nabla can be taken out, sorry, lambda as a constant factor. So w to w, and then it can be written as a nothing but here if it is nothing like I is a matrix, identity matrix, so it becomes 2wa or 2iw, simply 2w. So with this into account, and this is 0 because di are the scalar value, so this comes out to be 0 minus 2xi di as I mentioned, 2xi xit w plus 2 lambda w. Now you are equating this gradient or the derivative to 0. When you equate to 0, you get something like this, So w you take constant. When you w take constant, remember it's basically a vector. So simply if I take W, so lambda you cannot leave it alone. It has to be identity matrix has to be there, right? And this goes there. So W equal to xit plus lambda I inverse xidi. So this is the weight estimation for a single case. Now there are n number of cases if I consider all together. So this entire thing is nothing but it translates into this particular vector. So summation I equal to 1 to n, j equal to 1 to n, xi xjt this is, and this is nothing but rxx, which I have mentioned that they have directly, Simon has written that statement directly, plus lambda I inverse, and this is xi di is nothing but is a cross correlation kind of things. So you are having, and for the n cases, so I equal to 1 to n, xi di, this becomes rdx. Now, so that's why from that we got this entire relation for this, okay? So that's why I mentioned complete n. Now, where Rxn is the same is a time average, and remember that here negative things comes because where we write finally in terms of W map, if the negative is always there. Is the time average M cross M correlation matrix applied to the environment on the ith and jth experimental trials, and this is basically RDX is nothing but cross correlation, as I mentioned, cross correlation vector of the regressor and the desired response defined by this also. Now remember this and RxX and RDX are both averaged over all the n examples. That's why people call it a time average. Otherwise, there is no other time factor. So don't think they'll look for some time over there because it is average over the entire training example. That's why people call it time average. Okay. Now another question comes here. Suppose we assign a large value to sigma square W. The sigma square W is nothing but the variance of the weight space. If this value is large, so lambda comes out to be almost zero. Lambda comes out to be zero because lambda is nothing but sigma square by sigma square W. And but denominator becomes very large, so this is negligible, you can say equal to zero. So if that is the case, saying that prior distribution of each element of W is uniform over a very wide range of possible values. If that is the case, under such scenario, what is happening that this is zero, and then your map reduces to ML estimate. If you do conventional ML estimate, you'll be getting something like this. So ultimately, to say that if weight space is distributed over the large values, then there is no difference with the estimate using maximum likelihood or the estimate using the maximum a priori. So both are same. Okay, so this is what I mentioned this. In contrast, map estimate is basically, and also we have to see that ML estimator, that is maximum likelihood estimator, is an unbiased estimator. That is, if the number of examples are very large, then this estimator will be able to reach or converge to a value which is the true value. So this is what is called unbiased estimator. Whereas this map estimator is a bias estimator. So what do you mean by biased estimator? I'll just explain in another couple of minutes. So in improving the stability of the maximum likelihood estimator through the use of regularization, regulation means using the lambda concept here by incorporating the prior knowledge, because here we wanted to make stable, and so we incorporated this prior information, but it results into maximum posteriori estimator. This becomes bias. Now when I say bias, just hold on for a minute, I'll explain now, because this statement does not signify what you mean by bias. So this is clear, but this is not very clear. So just hold on for some minute. So finally, what we have to do that we have to have some sort of trade-off between the stability and the bias. Because to make it more stable, what we have done this, we have taken prior information. By incorporating the prior information, this estimator has become biased, which is not a good idea. So we have to have some sort of trade-off between the two. So we'll see this. What do you mean by bias? So in general, when I say bias, so bias of an estimator is defined as, here this estimator could be anything, means when I say here cap means is the estimated value, not the true value. So bias of this estimator equal to nothing but expectation of estimator minus the true value. Now let's see this here. As I mentioned this, all these things already. Estimator is said to be unbiased if this value comes out to be zero, which implies that the mean of this is nothing but this itself, right? So also we say that an estimator is said to be asymptotically unbiased if this is the case. So the MLE case which I have shown in the last slide, it is basically the case that asymptotically unbiased means as you increase the value of n to infinity, finally your estimator becomes the truly unbiased means it is the mean is going to be expectation of mean is going to be the W itself. So this is what I mean, but we'll see this. So with an example, I'll show that why it is biased or unbiased something. For example, that let's say these are some sort of samples and our IID that is identical and independent and identically distributed according to say Bernoulli distribution, which is nothing but given like this. You don't have to worry what is that, but let's say this distribution, which is whatever the distribution, it will be given to you. This is the distribution. A common estimator for this distribution is a mean of the training sample, which is defined by like again you don't have to worry from where it came. Let's say this is the mean for estimator. Now we have to determine whether this estimator is biased or not. So I'll show you the approach we have, which I have shown this. So why I've saying that bias of W1 is nothing but expectation mean of this minus W. If this comes out to be 0, then I'll say it is unbiased, otherwise it is biased. So let's see this. So example this same continuing. So this particular part as per the definition of bias, E of that, this estimator has to be substituted here. We can substitute that minus W means of course this W has to write here. And then for Xi is there, right? Now this one I have to apply E. And remember that I have told you while reviewing the probability theory that whenever I take the expectation mean of something, of a function, so I have to multiply that particular function with the density function, and then integrate or sum depending on the value is continuous or discrete. So this is the function altogether, and I have to multiply with the probability density function. So let's see this. So first of all, E has to go inside. So 1 by n and this E goes inside. So this is basically the value with which you want to find expectation. So I have to multiply with this. So here we know that. And so there is a xi, and these two values we are checking. This xi is either present or not present. So it's basically either 0 or 1. So this entire probability space is mentioned over here. It is mentioned right from where I've taken. This was given to you. This probability density function is given to you, right? So from that is the probability density function over there. And this is the probability part, and this is the actual xi. When I go for this, when you take xi one time as a 0, so this entire part becomes 0 plus xi 1, xi 1. So what will happen that this particular part will become 1. So basically finally it comes out to be W. So this entire part comes out W minus W. This comes out to be bias is 0. So we say that our estimator W is unbiased in this particular case. As I mentioned this you can do yourself. And finally this W minus W comes out to be 0. So this particular bias of this estimator is 0. So this is how you do this. So you can expect a some problem based on this. You can say that estimator is the given, check whether it's a bias or unbiased. So finally, I have shown you this entire fact means how a linear regression is designed and what steps we follow in order to estimate the weights of the linear regression. And there are two approaches. Either I can follow MLE or I can follow MAP. So there is certain condition on which a map becomes a MLE, right? And also I have shown you that why MLE is unbiased, whereas this map is a bias. So you can substitute those things for map and see whether it's really biased value or not. Okay, so I'll stop here. This completes this particular module here, and just a minute.